And welcome to another episode of Training Underscore Data. We're changing the format a little bit today because this is our first show that is completely virtual due to the ongoing self-isolation as a result of COVID-19. But despite that isolation, we actually have a lot of results and content that we've been putting out with CosmiQ and with SpaceNet over the last month, and with the wrap up of SpaceNet 5 and the launch of SpaceNet 6, we'll have a lot more coming. So stay tuned on this podcast over the next couple of weeks as we talk about work that we've either concluded or work that will be launching and occurring in real time. Today, we're talking about one of our favorite topics, which is SpaceNet. And specifically, we're talking about the challenge that we completed most recently, SpaceNet 5, which was focused on road network detection and optimized routing. And none other than the one, the only, the Colossus of computer vision, Adam Van Etten, is joining us again. Adam, welcome to the show.
Thank you.
And for those of you that may not remember, we did a original podcast on SpaceNet 5, the launch of it, back in August 14th of 2019, which seems like a really long time ago. But since the launch of that pod, we have done a couple of things. We've released the data set. We released the algorithmic baseline. Adam has single-handedly published 10 blogs, published 2 papers, open sourced 5 algorithms, presented at 4 conferences, and we're scheduling 1 training event. And so as my favorite Peloton trader, shout out to Matt Wilpers, says, you can't increase performance unless you're measuring it. And at SpaceNet, we've been trying to measure all of our work, and I'd say that Adam in particular, along with the rest of the partners, has been really busy in terms of making sure that we have a lot of great work and research coming out of this challenge. And I think with all these different things we've been putting out, it's before we get into the results and kind of what we thought were the key lessons learned, I think it makes a lot of sense to go back and talk about just some of the foundational pieces of this challenge, Adam. And why don't we start with one of the things that gets easily some of the most attention, which is the data set. For every SpaceNet challenge, we create a new data set, either that's in addition to the existing data or something entirely new. What did we do for SpaceNet 5?
Yeah, the SpaceNet 5 data set, we decided we'd do 4 more new cities. So we've done between 1 and 4 cities for all the SpaceNets prior. And the 4 new that we did for SpaceNet 5 brought us up to 10. So we're double digits now, which is pretty cool. And we labeled the road center lines. And so there's different ways you could label roads, but probably the most interesting way is actually label the center lines, which gives you the actual network structure. This is what people in OpenStreetMap do. So we're following the OpenStreetMap kind of guidelines. It's kind of a great way to do things. They have a good taxonomy that they've developed, so we follow that largely. But this is with professional labelers with some quality control. So what we found with some analyses we did later on was that these qualities seem to give us a little better results than OpenStreetMap. Again, not a knock on OpenStreetMap, but it's just hard to do. And so you kind of have to be motivated to get really high quality labels. And that's what we found here. And so we had these 4 cities. One thing that was pretty cool about it was that we had pretty high diversity. And so we had one of them being Moscow in the winter. So we got some snow involved there. That one is also fairly high off nadir. So we had some things at an angle. So there's some cases, or a lot of cases, where there's buildings actually kind of obscuring the roads. So that makes it tricky. Mumbai was another one. And that's also very different from Moscow, clearly. And that one is interesting because there's a lot of very small roads that kind of wind through neighborhoods. That's a bit tricky. San Juan was another one. San Juan's interesting, of course, because Puerto Rico is something that's been hit recently with some pretty heavy natural disasters. And then the final city was one that we called the Mystery City. We can talk about that later. I'll leave everyone in suspense now because I know everyone's sweating with this anticipation. And that was one that we held back for testing purposes. And there was a reason for that. Again, we'll get into that later. But between these 4 cities, we had 8,000 kilometers of roads, and we labeled not only the center lines, but some metadata tags. And what I mean by that is things like the properties of the road that you can tell visually, like how many lanes are there? What's the surface type? Is it paved or unpaved? What type of road is it? Being like, is it a residential road? Is it a highway, etc.? And from all that, with those tags and the center lines, you can infer like a safe travel speed, right? So this is something that it's not necessarily the government legal speed, but this is what we want to know for things like disaster response or other uses, where how fast could you safely travel on that road? And you can infer that with those tags pretty reasonably. And that is something that we could use to really ramp up the complexity of this challenge.
I think one of the things that was particularly interesting about the data set, or the new data, I should say, for this challenge was certainly we've focused on geographic diversity over time. But I think this was also the first time, if my memory serves me correct, where we also had real elements of seasonality, as you described with Moscow. And I think as we get into the results, that seasonal effect will jump out, and I think it's worth us considering as we're building out future data sets. And then so moving from the data to the algorithmic baseline, I think one of the biggest shortcomings for me personally, not for you, for me, is that we don't have a specific shirt made for the baseline. I'm frustrated about it. People have been writing me about it. And by people, I mean 2 people on Twitter, which constitutes a group. Why don't you talk through a little bit about what you did for the baseline, and then we can kind of roll from that into the evaluation metric that you obviously first created for SpaceNet 3.
Right. So with the data set that we curated for SpaceNet 5, we're hoping, of course, to go beyond, right, what we did in SpaceNet 3, which was also getting the road network out. And so the goal was to use these road safe travel speed estimates to have people pull out both the network and then the travel time / speed for each roadway, right? And this is something that hasn't been done before, from overhead imagery at least, right? And so there's been a lot of research in pulling out roads, less on networks, but some, which is exciting. But again, pulling out the actual speed of the road is not something that had been done. So we put a fair amount of effort into actually building this baseline that Ryan just mentioned to see if it's even really possible. Is this feasible? Of course, you can try, but if the results are complete garbage, it's not going to be interesting. So we tried a few different things with the baseline. I'll go over what actually seemed to work, which is first running a segmentation model, right? So this is often where people stop with roads, which is segmentation model, right? You put in your image and you get out a pixel mask where you say the background is background is background, and then the actual hit is the roads. So you have a mask where white would be roads and black would be background. That's a good place to start. That's not where we want to end. But you start there in this case, but then what we found is that if you have a multi-channel mask and then each channel is essentially a speed bin, then you can use this to pull out the road speeds. And we actually found this to be quite successful in the sense that we had a pretty low error rate in actually pulling out the speeds. Pulling out the road network is actually the harder part in a lot of ways in this case. Pulling out the speeds, we were quite successful, which was a surprise and a good one.
Yeah, and with the baseline, I think it's worth highlighting that this is something that, from a code perspective, you've worked on iteratively over time. And so you open source this. If you could just describe a little bit about that repository and kind of your logic in terms of building out for this challenge, because that's something that you talk a lot about in the blogs. I think for listeners here, it's at least kind of worth being pointed to if they're interested in that code specifically.
Yeah, so a lot of the code base is the initial piece. A lot of it was taken from the winning algorithms from SpaceNet 3, which was something that was a pretty good piece of code. And we started there, added some of those layers, added some increased post-processing. And the biggest thing, of course, is to actually get this road speed piece. And so we've also done a lot of work. We won't get into it here necessarily, but on making sure this scales to large areas, because if you want to do something actually useful, right, this has to apply to a large area, not just to some postage stamp region. So with all that in mind, we call this city scale road extraction from satellite imagery, or CRESI. So github.com/CosmiQ Cressy. You'll see the code base, some readmes on how to run it. And that is something we open source. We always do this for SpaceNet to make sure that people who are competing in these challenges have a good place to start, and they not necessarily starting from scratch, because as we discussed ad nauseum on this podcast, right, the barrier of entry from computer vision scientists to geo is pretty darn high, and we want to try and minimize that and let people focus on more the computer vision part. And so again, this is the way to do it. Of course, we see people improving upon us all the time, which is what we want, but that's maybe a good starting place to see how you could get started pulling out roads and speeds from imagery overhead.
Yeah, and to give some context on the baseline, this is something that really in the last year, I would say has matured dramatically, based in part upon our challenge participants' work as well as your work, Adam. And it was really, I think, compelling, and we'll get into the challenge structure and the results here in a second, but it was really compelling to see how strong the baseline was as a start. And that's something that's a little different for us historically relative to the other 4 challenges. And I was trying to think of like an analog, and I was watching a 90s sitcom recently. I won't say which one. It wasn't my choice. I'll just leave it at that. But
it was Friends, wasn't it?
No comment. I'm not gonna talk about it. But in the show, they have MapQuest. For those of you who remember MapQuest, but there's MapQuest reference in the show. I would say if there was a Turing test for Cressy, I would say you have surpassed the MapQuest test in terms of routing optimization. So I think that is, it's not the destination necessarily, but it's certainly a good benchmark. And since we've crossed that level of maturity, it's always important to kind of step back and ask, why are we even doing this? There's the direct application, right, for mapping. That's obvious. There's obviously a large community that we want to continue to serve, both on the research side and practitioner side. But I think one of the things that's really compelling about roads, and Adam, you've kind of continuously reminded me and the other SpaceNet partners about this, is that there are applications beyond, far beyond in some cases, just mapping for geographic or GIS applications. Why don't you talk through a little bit of that and why we think this particular challenge, and specifically optimized routing, is an important next step?
Yeah, I think a lot of the initial motivation for us was from talking to some of our colleagues actually who work kind of in the pandemic response area. And one of those was, look, if there's an outbreak, say in a region, this is obviously very topical, and I didn't even pick this one. This was one that actually is something we talked about for years, is how do you get supplies and personnel to the area in need? And if that area is poorly mapped and there's maybe seasonality, say there's flooding or there's snow, can you rapidly pull out the road network and the optimal routes to get people there? Because when time is critical, what maps you might already have might be outdated, and mapping those by hand with people is a very slow process, right? So if you can do this with satellite imagery, that could very, very much help these processes of humanitarian response. So that's one, and that's not going to change in the near future that we can see. That's still something that's going to be a need, and something that, if we can do a good enough job with this, then we could help with that. Another one, though, is that there's increasing attention really from commercial space in the automated road network extraction and the optimal routing piece. So, self-driving cars is one where you need very high fidelity maps to actually have a good autonomous vehicle. And if you can pull out the actual road center lines with high enough precision, that's a huge help, especially in maybe rural areas that aren't perfectly mapped, and you can't rely on just 1,000 cars going down the same roadway every day to build up that really high quality center line. If you can't do that for whatever reason, then something like remote sensing, specifically satellite imagery, can be very beneficial. And then we've seen increasing interest again, even from auto manufacturers that are trying to do this, that they really are intrigued by this idea.
Yeah, and that was certainly something that came up as a topic when we presented at the Detroit Auto Show last year. And even more recently, some of our partners, in this case specifically, Maxar, they released their article recently with the Toyota Research Institute.
Right.
I think this is a timely topic that's going to continuously come up. And I hope at least both the data set and the results from this challenge can help drive thinking around some of those more automated solutions. So one not so important question before we get into the challenge structure, Adam, is it oxymoronic to say an autonomous Subaru? It seems like why would you have that? I'm just curious.
No, I think maybe an autonomous WRX. I think that seems a little silly. The
right.
other ones, no, that's fine.
So everyone else good. WRX doesn't get the.
Nah, you can't. That thing's analog. It's an old school dinosaur.
Well, with that, let's get into the challenge structure. I think each challenge, that we do, and people have heard this on this podcast multiple times, so I don't want to get too in the weeds on it, but we try to increase the analytical complexity. I think what was particularly interesting about this challenge, the way you structured it, was that we kind of had a couple different knobs that we turned. Normally, we only turn one.
Right.
As an example. In this, we kind of turned two with the structure itself. Why don't you talk about that a little bit?
Right. So the first knob really was looking at the timing piece for road networks, and that was interesting for the reasons we just talked about. Right. Doing actual optimized routing, not just shortest geographic distance, is important. But what that means is that all the existing metrics, even the ones we'd worked on for SpaceNet 3, weren't quite appropriate, right? If you want the actual timing aspect and not just the geometry of the road network, those existing metrics just don't address that at all. And so what we had to do was to modify the APPLES metric. Remember, APPLES stands for Average Path Length Similarity. And the modification was that the path length no longer is distance, but it's time. And so you're trying to optimize the time from point A to point B with this metric. And that was kind of fun because that we have now a metric where we can measure this. And that's something that we hadn't really found out there in the literature to do. So that's one knob. So it's kind of a new metric, a new goal. And then another one was trying to address kind of a frequent criticism that you hear from public challenges, which is people do very impressive things and they build very highly tuned models that work great for the challenge and don't apply at all to the real world. And so they're not really of any utility besides maybe some interesting algorithmic work. So one way to address this, right, is especially for what we're looking at in the GIS space is, can you build an algorithm that will apply to a new geographic region? If you can do that, then you have a chance to actually address these problems we want to help address, which is, let's look at like a disaster area that no one has a good map for. Can you actually build something that works there? If not, this is somewhat academic, right? So there's lots of ways you could tackle this. I think the most straightforward one is just to say, all right, we're going to train, we'll give you these cities to train on, and then we'll give you other cities to test on. And you won't even know what some of those cities are. And therefore, if you overtrain and hyper-tune your algorithm to work on only certain specific cities and geographies, you're going to fail. And so that was the second knob was, again, just to do that. Say, like, unlike previous SpaceNet challenges, we're going to test you on an unseen geography and see how you do. And that was a lot of the frustration from the competitors, frankly, because they didn't like that. But it was cool to see how well they did, actually. At the end of the day, it actually was encouraging. And we have algorithms as a result of this that seem to deploy pretty widely across a broad area or broad diversity, really, of geographies.
And although it's public, we haven't said it here. What was the mystery city?
Mystery City is Dar es Salaam in Tanzania. So it's a very large city in Eastern Africa, and actually kind of cool because a lot of that region is also covered by the Open Africa project. So there's some overlap there, which we didn't use for the challenge, but it's cool to have that overlap in labels. And so it's a very different city from the other three, right? That's very different from Moscow, from Mumbai, and San Juan. So the diversity there is pretty high.
Yeah, absolutely. And I think maybe it's not a third knob, but maybe a knob and a half of one. Is also, this is a subtle change in the challenge structure rules, but we also changed, and I thought this was particularly interesting, the amount of time we give for retraining to the final submissions. And I think we're going to talk about that later and why we did that, but I think it's worth giving a nod to that here, because that was kind of another sort of structural change that we made that was perhaps different than certainly the last 4 efforts that we've run to date.
Yeah, and that was something that we really started thinking over highly after SpaceNet 4, where we saw people inputting models with like 18 different deep learning models, a huge ensemble, and you get like a tiny bump in score, but a huge penalty for runtime. And so we dialed back the allowable training and test time just to try and address that as well. And we saw people still did that, but just a little bit smaller this time. And as Ryan intimated, we'll talk about it even more later about, is it even worth it, even with the knobs that we turn now?
Yeah, and so let's jump into the best stuff right now, Adam, because I think one of the things that we have done a little bit more by accident than design initially, and I think it's certainly become part of our strategy as a collective in the last year, is to do really robust analyses after each challenge. And I think we get better at this with each one. I think the analyses that you did, the really 4-part series on our blog posts, the downlink, I thought that was great. So there's a lot of content there, and I would say for any listeners on the show, go to the downlink. That's downlink with a Q. That's our main blog. You can find it on Medium, or you can also find it, a link to it on our website, which is just cosmicworks.org. If you want to see all the metrics or figures that we're going to be talking about here. But essentially, Adam, in your multiple posts, you kind of break out the results in a couple different categories. And I think one that you look at is sort of geographic diversity. Another the second is sort of scene or chip level variance, which I thought that was really interesting. And I want to dig into that a little bit more. I think third was sort of the road network feature variance. And then last but not least, which we were just kind of intimating with the challenge structure, was performance versus speed.
Yeah.
So we can kind of dive into each one of those. And certainly, like I said, if anyone has interest, please go to the blogs and kind of read or reach out to us if you have any questions. But why don't we start with geographic diversity first, right? We talked a lot about that as part of the motivation for building the data set. What did that mean or not mean from a performance perspective for the competitors' submissions?
Right. So we had these 4 cities, and we had really only Moscow and Mumbai released for training. We had the SpaceNet 3 cities as well. So they had 6 cities total to train off of. But for SpaceNet 5 testing, we tested on all 4 of the SpaceNet 5 cities, right? So we tested on Moscow, Mumbai, San Juan for the first round. So there's a public test that established the leaderboard initially. And then the top competitors then are retrained and tested on the final test set. The final test set includes all 4 cities: Moscow, Mumbai, San Juan, and Dar es Salaam. And what we found was, as you might expect, there is a variance in scores among those 4 cities. So some are harder than others, right? Dar es Salaam actually turns out to not be the hardest city. So this is something I'm kind of hitting the punchline right away, which was there's part of this is due to San Juan to Dar es Salaam not being a super hard city. That was intentional on our part. We didn't want to pick like Moscow, that was totally different with snow, as the unseen city, because that would have been pretty mean, frankly, on our part. But people did a pretty good job of building models, at least the winners did, of building models that applied to an unseen city. So what we saw was that scores for Dar es Salaam were comparable to the others, which is pretty cool. And so that diversity actually was a success, I would say. The way we structured the challenge, we showed that you could build a model that would deploy to a new one, to a new city. The other thing that was interesting was there's a very small spread between fifth place and first place. So we scored the Apple's time metric, time being the actual route length definition. And in that sense, the fifth place score was 0.45 and then the winning was 0.48, right? So spread of 3% there between fifth and first. The baseline was right there at the fifth place as well. And so that's a small spread, even though there was a somewhat a variance in the algorithms applied. The interesting thing, or one of the interesting things was though, that if you look at the scene by scene scores, right? So what we do, just to remind everyone, is we split all of the testing area into small 400 by 400 meter chips. We score each one individually. We add those up and aggregate them, and that's the final score that people get. And so if you look at the score for each scene, there actually is a very large variance among all those top five. So even though they kind of add up to be very similar scores, there's a huge variance intra-scene. And that was interesting and surprising. And a lot of the reason is frankly that, especially for smaller networks, which is what you get for this 400 meter chips, it's a somewhat chaotic process, meaning small changes in variables and small misses of a road can have a large impact on your score. And this is intentional, right? If we want to actually really penalize people if you miss a connection in a road network. We've gone into this in detail before. I won't go into it now. But what that means is that small changes in your network can have pretty large swings in score. And that's what we saw was that we see this huge variance in an intra-scene, even though they add up to be similar. That's kind of interesting, right? I don't really know. It's hard to actually figure out how to use that information to improve scores, but it's cool to know that. It's something we're thinking about going forward.
And on that point, Adam, this is just more of us just postulating here, but given the sort of difference at the scene level, do you view this potentially as sort of an optimization problem at this point, where we kind of take the best of each individual model and how they perform at different scenes and sort of figure out how to build sort of a more refined model, or is this still sort of in what we see in a lot of our previous challenges, which is more of there's still just a lot of fundamental work to do? I get the impression, just given some of the performance we saw in some of the cities, that it seems more like we're entering an optimization phase, but you have a better sense of this than I do.
Yeah, I'm not sure we're quite there yet, because the reason I say that is I would have said the same thing, I think, but the way that people construct their models with these large ensembles is they're kind of already trying to do that, right? So by ensembles, again, we mean that you're training maybe up to 12 different models, combining them, and then getting the score out. And so I don't know if we're quite there yet. I think a lot of the issue is that there's some post-processing techniques which have a very large impact on score, and I think haven't been really highly focused on. So people tend to focus on the deep learning architecture, partly because that's what people get excited about, right? I mean, try and go to a computer vision conference and publish a paper about post-processing. They'll laugh at you, right? But in this case, I think that actually is the key part. And so that post-processing, I think, has not been analyzed well enough, even by us, frankly, to really have a good sense of how to combine things in an intelligent manner.
Yeah, and just to maybe provide some color to it, I was really surprised at the scene level, at the variance in scores when competitors were looking at tiles that were featuring dense urban areas. That's something where I would have thought there would have been more uniform responses. There wasn't. I just thought that was really interesting. I'm curious if there's sort of anything to add on to that.
Yeah, I mean, part of it is it also varied between city, right? So, for example, like scores in San Juan are actually higher than Moscow, but there's less variance in Moscow, and so there's again, that's hard to unpack what that all means. But I think part of it is that like if you have edge effects, meaning like kind of roadways near the edge of your chip, or difficult to spot intersections, that can really impact your score. And if you pick kind of simple post-processing methods, which most people did, including our baseline, I'm not throwing stones here, if you pick the wrong threshold, in some scenes you'll be great, some scenes you'll screw it up terribly, right? So I think that really there's a bit of work to be done on this. By post-processing, let me clarify. What I really mean is there's a multi-step process to pull out your segmentation mask into a road network, right? I won't go into all those steps, but a lot of that is probably one of the key ones is there's going to be gaps in that segmentation mask for whatever reason, something like an overhanging tree or intersection, right? Or how you try and fill in those gaps has a massive impact on your score. And we haven't seen anyone really have something significantly better given the closeness of scores, that everyone's picking something similar. And again, that's partly on us, right? We established the baseline. The baseline was actually pretty good compared to the winning scores, which is cool. But perhaps we overprescribed the solution. Of course, we didn't make anyone use the baseline, but people kind of went down that route. And we can talk about it later, but there are other techniques out there people are working on. They're very different from what we tried here, which maybe have different failure modes, but that would be cool to see kind of how they compare to this method, where the failure modes that we saw, and have a decent idea why they failed, but how to fix them, that's a different problem.
Yeah. And kind of changing gears a little bit, but not much, is I think you see this same sort of challenges when you get to the variance and feature labels as well, in terms of what really tweaked performance with the models. And why don't you talk a little bit about the actual road network features that had the biggest impact on the score? Because I think that if you're thinking about kind of the big takeaways from here, we've talked about two of them, that's really the third one, which I was surprised at the results that came out of this, to be perfectly blunt.
Yeah, for sure. And before I talk about that, one more point about kind of the intra-scene piece, which was one thing that we saw, which was interesting, right, is if you look, so remember, public test was on 3 cities, and then private test, the initial test was Moscow, Mumbai, San Juan, and the final scores were based on those cities along with Dar es Salaam, but different regions of those other three cities.
Yeah, that's an important point.
And what we found, kind of surprisingly, we were surprised by it because it hasn't really been seen in other SpaceNets quite as much, was that in Moscow, Mumbai, and San Juan, all cities that had been seen before and tested before, a significant drop in score for the final test, which means that even in the same city, neighborhood level details really matter.
Yeah.
And so, and that is a huge takeaway in the sense that the drop in score from seen test areas and unseen test areas in the same city was actually greater than the difference in score for the unseen city.
Yeah.
So it's maybe hard to unpack what I just said, but our takeaway was that kind of neighborhood level details, such as say maybe number of roads or other features, which we'll talk about in a second, is more important than like kind of the citywide geography or vegetation or things like that. And that was a surprise, frankly, that matters as much as it does. And so that's important to know that, like, if you train a model in Moscow, great. It might not work on, it might not even work on southern Moscow, right? In this case, that was kind of what we saw. Same thing for San Juan, right? We train on Western San Juan, Eastern San Juan. Even though it's the same darn city, it looks different enough that scores dropped significantly. I mean, we're talking about like 15% drop. So
Yeah.
that was a surprise. That's cool to know that you have to be aware of that even if you have 100 different regions, say we have 10 now, then you have 100, you can't necessarily even say that you work on the same city, because these neighborhood level details really matter, at least for road network extraction.
Well, and I appreciate bringing that up because, from the sort of the operational context, that means that if one is building out a data set of any particular geographic location, that having a very rich representation of that location is critical. And
Yeah.
so that normally what that translates to roughly is that you have to have probably more labels for any one area than perhaps you thought. And then two, you actually have to, any end user would have to start thinking through what constitutes a fully representative label set for the area they care about.
That's right.
And so not only is it just a matter of locations, as you're saying, but making sure that you have a robust enough representation in each area. I mean, I think that it's one thing I don't think anyone would maybe disagree with that from like a high level logic perspective, but being able to quantify its impact on a particular application, I think is very novel. And
Yeah.
I think it's fairly telling how much the scores change on that. So once again, kind of going back to almost the early days of why we got started, having more richly labeled data sets is, for at least for the time being, is still really critical for this type of work.
Yeah, it's true. And that sounds maybe a bit pessimistic, but on the upside, right? Given what we saw with applying these models to Dar es Salaam, I think what you can probably say is if you have a fairly diverse data set, in this case, we had 6 cities, that's not terribly diverse, but it's decent, that a new unseen city, or in this case, a new unseen part of the same city, you can make a reasonable guess that you'll have a score that's, probably about the worst you saw, right? So I think I'm not being very clear. I certainly agree with your point, Ryan, that like you need a very representative data set. But what you can't say necessarily is if I have some of Moscow and it scores at a 0.58, which is what we had, then a new part of Moscow will score 0.58.
Correct.
You can't say that. But what you probably can say in this case was the worst I saw for testing was about a 0.45 or something. Inferring on a new region, be it the same city or a different city, I'm probably going to get about that score. That's what we saw. So you're going to see a drop in score, but it's not going to be just a complete disaster. So those are kind of two sides of the same coin, but it's good to know that. And again, the fact that we can quantify it is kind of fun.
Yeah, absolutely.
And going in the next step, right, then at least in our mind was, okay, we see these variances and these kind of behavior we didn't expect, but it's kind of exciting. Are there any features of the road network which actually are predictive of this, right? Beyond just kind of guessing, oh no, why this changes. So what you can do is build a fairly simple model where you're taking as inputs just the features of the road. In this case, we picked just a handful, like number of unique speeds of the road, number of intersections, length of the road in kilometers, maximum speed, minimum speed, things like this. Those are features. And then the predicted value is just the Apple score. Can you build a simple model to take those input variables and predict the Apple score? In this case, we built a random forest model for that, and actually it was very predictive, very high score, R-squared score of 0.95 or something like that. And then you can take that and say, okay, actually, given a road network, given these 8 simple features that we can calculate trivially for the road, I can have a pretty good guess how well a model would predict that road network. That's really cool. But then you can also go into farther and say, well, what features determine that score? So we can do that, determine the feature importances for this random forest model. And what you find is that there are features that are predictive. In this case, the 2 most important are just the length of the road. So the number of kilometers of roads in the data set has a huge impact. And that maybe will seem counterintuitive, but if you think about it a little more, it makes some sense in that if you have a very sparse road network and you're trying to do routing and you screw something up, one intersection, you're host, right? Whereas if you have a larger road network with more intersections and more roads, if there is a goof somewhere, you can route around that, right? And since we're actually at the end of the day measuring routing with the Apple's metric, it makes some sense that with a larger road network, you would have a higher score. That's pretty cool. And then the other feature that's pretty predictive is maximum speed. And that's a little more surprising. Why would a higher maximum speed in the road network mean a higher score? Part of it is those are correlated with number of kilometers of roads. But the bigger thing, I think, is that these kind of diverse road networks and higher speed let you, I think, do a better job of routing through the network. And that's kind of hand wavy. I won't go into too more details now. But again, knowing what those are, that's really the big takeaway. It's kind of fun to be able to pull out those features which are important for road network extraction. That's something I didn't know before.
Yeah, and I think it makes sense, certainly, when you put it all together to say, for example, I'm going to be looking at a really densely packed central business district, for example, that maybe is filled with not only a lot of building layover or things like that, but also very short roads. That becomes, or very short length roads. That becomes a really challenging problem for one, finding those networks, but then also if you miss one road, then you miss potentially several intersections at once. So when you put it all together, it becomes pretty clear where I think some of the next level research has to go in terms of what should be focused on and what we think is kind of good enough for the time being.
Yeah.
And so, last but not least, and this is something that, I'm, as you know, Adam, and as most of you know who have probably listened to this pod before, I'm particularly passionate about is when we talk about performance versus speed, because you kind of get into this sort of bigger discussion that you see both in AI topics in general, certainly in geospatial analytic topics as well, which is how do we take things that are in the applied research domain and also start using them in real applications. And I think what we're highlighting here, and Adam's done a really good job with it, is there's certainly a lot of applied work that still needs to be done, as we're just saying, but there's also now kind of getting to a point where we can say, are these models perhaps good enough for certain applications, maybe even as a first look? Performance versus speed dictates a lot of that, because certainly when you get into any sort of commercial or mission application, you cannot be running massive models because it's just not computationally efficient, or the time just simply isn't there to do that. So Adam, walk us through a little bit of that.
Yeah, so we did kind of as the final piece for SpaceNet 5 when we released the models just a couple weeks ago. We also just did a comparison just to triple check the runtime for each one. And so we have the scores, obviously, we know the baseline was about a 0.45 and the winning score was a 0.48 out of 1, right, for Apple's time. And just as a segue real quick, that is heavily weighted on the unseen city of Dar es Salaam. And so those scores might not seem that great if you instead only like subset seen cities and larger road networks, which we already showed are actually highly performant. You get a much higher score. And so these scores are actually pretty good if you look. It's maybe like a 0.7 for these kind of easier road networks, which is definitely good enough. You can do some initial routing. Not perfect, of course, but in our estimation, good enough maybe to get started and to help people start with a road network. Maybe they can maybe hand label later or something. I won't go too much down that road. We could spend a whole podcast talking about it. Anyway.
Future idea right there, Adam.
Yeah. So we see pretty decent performance at the end of the day. In our estimation, we were impressed and surprised with the competitors, how well they did. But the standard method people take is this ensemble of models where you train between, what was it? I'm looking right now. It's between 4 and 12 deep learning models. And then you ensemble these and then you figure out your final prediction. The baseline just had one model. And of course you're incentivized to do this in a challenge. And even though we dialed back the allowable commute, people still filled up what they could, as you should if you're trying to win. But what's interesting is that if you actually do the comparison of runtime versus performance, in our estimation, these ensembles maybe aren't worth it. So the numbers are, the baseline was about a 0.45 for score. That runs at about 10 square kilometers per minute on in our case, an old NVIDIA dev box, right?
Don't speak ill of the dev box.
I'm not. It's kept me alive. So anyway, there's faster GPUs out there, but that box, you're running it at around there, 10 square kilometers per second. The third place score, or second place score rather, was at 0.6 square kilometers per second. So 15 times slower for a 3% boost in score.
Yeah.
And so that is something where you have to decide, frankly, as the end user, if you really need that high score, then go for it. In most scenarios, that's probably not worth it. The winning score was a little faster, which is great. It was only about, 6 times slower than the baseline model for a 3% boost in score. But still, 6x slower is a problem. And this isn't meant to speak ill of the winners, right? Because again, they weren't required to have it be fast necessarily. And I'm confident that if we made that a part of the metric, then they probably could have done a lot better. But it still speaks to very minimal boost in score for a lot slower algorithm. And this is something that I think people fall into this trap very frequently. I think in academia, where usually you're incentivized to get that boost in score. You add layers, you add layers, you add layers, you add layers, you get a 3% boost in score, you publish, boom, off the races. That is interesting. That is progress. But it's dangerous if you can't actually use it in the real world. Yeah. And so we are pretty excited to see this trade-off. And again, it's up to the end user how they want to take this information. But often this boost in score is not worth the extra ensembling time in our estimation.
So kind of putting all this together, Adam, you've obviously, you served as the challenge manager for SpaceNet 3 as well. So you've really been kind of pushing us along the path of roads work for almost over 2 years now. It's hard to believe. What are some ideas you have about either future work or other trends that you're seeing in either the academic or commercial area that's either kind of building on the type of work we're doing or at least tangentially related?
Yeah, I think one marker of success that we're pretty excited about is the increasing number of papers that we're seeing in academia, both using the metric that we've been using as well as the data set. So certainly road network extraction from satellite is still kind of a fringe research area. But again, it is increasing in number of people working at that. That's pretty cool. And the number of people using SpaceNet is also increasing. So we're excited about that. And that especially lets us really view the trends even easier because we're familiar with the data set. And one is that the method that we propose as a baseline and a competitor is used is this kind of multi-step approach of segmentation and then network extraction, post-processing, speed extraction, which at the end of the day actually is quite performant and compares well with other techniques. We've actually done the comparison, so it actually works pretty darn well, and it's pretty darn quick. But going directly from the imagery to the graph in like a kind of unified algorithm is something that people are increasingly working on. And that is something that's super exciting. So we've seen, again, a few published papers doing this with SpaceNet data, not always SpaceNet data, which is fine, but sometimes they're using it, which is cool too. And those are really exciting to see. To date, honestly, those haven't been really highly more performant than what we see with our multi-step approach, but it's more elegant. And I am excited to see as those improve, then they will hopefully kind of surpass the performance of this multi-step approach that we've explored. I'm not sure, to date, they're also much slower in terms of runtime. But again, ideally, you kind of want a unified algorithm. And this is, to segue for a second, right? This is kind of what happened with object detection, say like 5 years ago, right? You had these multi-step approaches, people kept iterating, getting better performance. And then finally, a few people said, you know what, we're just gonna have a unified all-in-one algorithm. And when they did that correctly, you had things like YOLO, which was way faster and way more performant than everything else. So that's what we're hoping happens here. I don't know how far away we are, but the fact that people are using data and looking at this problem from like a reinforcement learning perspective, for example. So Development Seed, some of our colleagues there had a really cool blog recently about that.
Yeah.
Where they're looking at reinforcement learning to pull out road networks. Super cool. So that idea, again, still in some of its infancy for this road network extraction piece, but the fact people are looking at that, super excited about that.
Well, Adam, it's been awesome. You've done great work on this. It's been big for all of the SpaceNet partners as well. Thanks for all your work on getting us one step closer to optimize routing, and excited to kind of see what other work comes out of this with both the data set and the code in the coming months.
Yeah, definitely. I think it's a cool time.
Well, excellent. And thanks everyone for listening today. We'll have active links on either the websites or blogs we've mentioned today in podcast descriptions. Make sure to check that out. And also, as we continue this sort of work from home environment, make sure to also check out one of our colleagues, Jake Schermeyer, who was recently featured on Adam Simmons' Project Geospatial blog or podcast talking about SpaceNet 6. And once again, big shout out to our partners at Hardcast Media for helping set up today's virtual podcast recording. Thanks all. Take care.